So we ended with trying to identify which way the equilibrium will lie based on the relative strengths of the acids or the bases present. It doesn't matter who you choose to focus on. So we're going to practice that again a little bit more right now, and then we'll move on to new stuff. Oop, thank you. So the first thing you're going to want to do is to identify your conjugate acid-base pairs. So who's the acid, who's the base, who's the conjugate? Okay, so if you remember the Bronsted-Lowry definition of an acid is it loses or donates a hydrogen ion, and then the base accepts it or takes in the hydrogen ion. So this guy looks like it's a base because, oops, I'm going to go on this one. It gained a hydrogen ion. And sometimes it's helpful for water. If you want to see it easier, you can rewrite it as HOH. So you can see how it lost the hydrogen. So that's what makes it the acid. And then this guy is its conjugate base. So now predicting which way the equilibrium lies, you either have to compare the two acids or the two bases. So let's compare the two acids first. And then you should still get the same result for the two bases. So basically, you're trying to pick who the stronger acid is, because the stronger acid will be the thing that loses the hydrogen ion. Okay, it will be the one that gets to lose the hydrogen ion. So we go to our chart. Again, you cannot do these problems without either K values or a chart. There's no way to do it without that. So we have who? Water and H2PO4 minus. Okay, so acid, these are our strong acids up here. This is as strong as it gets. So the closer you are to the top, the better of an acid you are. So strong acid. So H2PO4 minus is right here, and water is down here. So H2PO4 is the stronger acid. So it will be the thing that loses the hydrogen ion. So you have to go, okay, well, what happens if it loses the hydrogen ion? Well, it turns into this guy. So we are heavy on the reactant side. So the equilibrium lies to the left, where we call K less than 1. Why? Well, K is products over reactants, right? So if you have a lot of reactants, your K is going to be, small. Now, we didn't have to look at the acids. You could have focused on the bases. So let's get you should still get the same result though. I mean, it wouldn't change, but let's look at bases instead. There's no reason you couldn't have focused on the bases. So my two bases are right here, this guy and this guy, conjugate base. And we want to pick who the stronger base is. The stronger base will be the one that gets to accept the hydrogen ion. So you go to your chart and you find HPO4 2 minus and OH minus. Now notice that the basic side is the other side of the arrow. So we're looking for, so this is a strong acid, this is a weak base, conjugate base. So as this gets more acidic, it gets less basic. But as these get least acidic, it gets more basic. If you're a weaker acid, you're a better base, okay? So look at hydroxide on this chart is at the actual bottom. It's the strongest base on this chart. Okay, HPO4 2 minus is right here. It's a decent base, but it's not as strong as hydroxide. So if you're thinking of like a winner, hydroxide gets to gain the hydrogen ion, which would form water, aka more reactant. More reactant, equilibrium lies to the left. The reactant side, K is less than 1 or small. Okay, let's do one more practice. So let's identify conjugate acid-base pairs. This is the acid. Why? Because it lost a hydrogen. So this is a base, this is conjugate acid, it accepted a hydrogen. And again, we can either focus on the two acids or the two bases. It doesn't matter. So let's look at the acids first. We're going to figure out who the stronger acid is. Is it ammonium or is it water? So we go to our chart and we see, okay, well, water's the worst acid on here. Ammonium is a little bit above it, so ammonium is the better acid. So ammonium will lose the hydrogen ion. Well, when it loses the hydrogen ion, it forms ammonia. So equilibrium lies to the right or to the product side. K greater than 1, right? Because if we have more product, you'll get a bigger number. So what if we would have focused on the bases? Compared the relative strengths of the bases. Hydroxide and ammonia. So you would go to your chart. Hydroxide is the strongest on here. Ammonia is still, it's down there, but hydroxide is stronger. So hydroxide accepts the hydrogen ion. Well, when it accepts the hydrogen ion, it turns into water. So equilibrium favors the right-hand side or the product side. Any questions on this? Okay. So binary acids are acids that just have two different elements in them. Don't confuse it. It doesn't mean you have two elements only. It just can be two different elements. So like H2S is a binary acid because it has hydrogen and sulfur in it, okay? H3N is a binary acid because it has hydrogen and nitrogen in it, two different elements, okay? So if you have a binary acid, as you move down a family, the acidity increases. So the strength of the acid increases. So you have to remember that to be a good or strong acid, you have to be easily willing to lose a hydrogen ion, okay? So the easier a substance can give up a hydrogen ion, the stronger of an acid it is, all right? So this is going to be the reason why a lot of kids, we always think HF, or it's easy to think it's a strong acid, and it's not, it's weak, and this is going to be the reason. So of the halogens with hydrogen, HF is the weakest and HI is the strongest. So it's going to have everything to do with radius, okay? So you've got like fluoride, oops, and then chlorine, chloride, and then bromide, and then iodide. And these are all hooked up with a hydrogen, right? Okay. So fluoride is the smallest anion in that family, which means the hydrogen and the fluoride, when they're bonded, are actually pretty close to each other. Well, if they're close to each other, they experience the electrons experience a really strong Coulombic force. So like it's hard to rip that hydrogen away from the fluorine because they're so close to each other. Whereas I is huge, okay? So the H can only get so close to the I. So because of that, the H is easy to pluck off. It experiences a weaker Coulombic force of attraction because of the size of the iodide ion. And therefore the hydrogen can be removed easier because it's not held as tightly. And the ability to be removed easier makes you a stronger acid. So the easier you can rip a hydrogen off of something, the stronger of an acid it is. So this is the reason why HF is not strong. The H and the F are just too close to each other. The HF would rather be bonded than for you to be able to let it rip off a hydrogen ion. Okay? So again, this is also the same concept of their conjugate bases, right? If you have a weak acid, its conjugate base is strong. So let's do HF, for example, and then I'll do HI as the other example. So like the F minus, right? So this is a weak acid, and remember, weak acids have strong conjugates. So like this conjugate is such a strong base that it sees this hydrogen in solution and hooks up with it and reforms this guy. So it's like it tries to break apart, and the fluoride's like, yeah, no, and it hooks back up with the hydrogen to reform this guy, which is why it doesn't allow much of this to break apart. So yes, it'll ionize a little bit, but really the second it tries to ionize, the fluorine hooks back up with the hydrogen to reform HF, which is why most weak species remain intact as opposed to ionized. Now the opposite of this is true for strong acids, right? A strong acid produces a really weak conjugate base. So the iodide's in there and it sees the hydrogen, but it's like so weak that it can't really reattract the hydrogen to reform HI. So it just stays ionized. That's why strong substances stay ionized, because their conjugates are so weak that they can't, or strong acids stay ionized because their conjugate bases are so weak that they can't like go back and hook back up with the hydrogen. So they just have to stay floating around as ions. And then again, why is that? Well, the fluoride ion is strong because it can get to approach H closer. It's smaller. So it can like yank it in easier. Whereas the iodide's like this big bulky thing, and it like has a really hard time trying to re-yank in the H plus. Okay. Oxyacids, I kind of briefly mentioned when we did the Lewis structure chapter. So oxyacids are just acids that have oxygen in them. So you see these a lot with your polyatomic ions. And so you have an H. Now be careful because the acidic hydrogen is always attached to the oxygen, or oxygens if there's more than one, in the oxyacids, okay? So like sometimes the way we've generally learned it is like H is +1, right? ClO minus is -1, so we write it as HClO. But you'll sometimes see it written as HOCl. This is the same exact substance. They're just showing you that the hydrogen is hooking up with the oxygen as opposed to attached to a chlorine. So that they like try to write it in the order that the elements are bonded in. And again, this Y is some sort of other element, like a chlorine or a bromine or a nitrogen or a phosphorus or a sulfur, just something that's not oxygen, okay? So sometimes we have multiple oxygens, like 3, and we'll talk about that in a minute. But however electronegative Y is, the more electronegative it is, the stronger the acid is. And the reason that is the more electronegativity will cause the electrons to be pulled away from the hydrogen. So like HOCl. Okay? The more electronegative this guy is, the more the electrons are being pulled this way. Well, the more the electrons are being pulled this way, the easier it is to like, whoop, swoop in and yank off the hydrogen because it's not held as strongly. Okay? So between these 3, this would be the strongest acid of the 3, because chlorine is the most electronegative relative to bromine and iodine. And so it pulls the hardest on the electrons relative to the other 2. So it's easier to remove hydrogens, the hydrogen atom from the acid. Again, the easier you are to rip off a hydrogen atom, the stronger of an acid you are. Because producing hydrogen ions in solution is what makes something acidic. Okay? So again, this is just what I said. HOCl would be the strongest and HOI would be the weakest. It attracts electrons the weakest, so the hydrogen would have a harder time being ripped off. Okay. The more oxygens you have, the more acidic the acid is. The reason that is oxygen is the second most electronegative element on the periodic table, right behind fluorine. It's fluorine and then oxygen and then nitrogen. So the more oxygens you have, the more pulling away of electrons you have from the hydrogen. So in fact, this is kind of interesting, right? We have HClO. This is HClO2. Wow. This is HClO3. This is HClO4. And this guy's one of our 6 strong acids. And that's why, because it has all those oxygens on it. All these oxygens are just like pulling electrons and pulling really hard, and that hydrogen's like whoop and gets ripped off easier. So the more oxygens in an oxyacid, the stronger the acid is, because there's a huge, or the more oxygens you add, the more difference in pulling and electronegativity you have, because oxygens pull pretty hard on electrons. So they'll pull the electrons away from the hydrogen, making the hydrogen not held as tightly. Okay. So organic acids are all weak. They have carbons and hydrogens and oxygens and sometimes nitrogens and other things in them. So they're represented like this. This is what is called a carboxylic group, or a carboxy group, the C double bond O OH. Okay. This R just means any carbon chain attached to it. Okay, it could be any sort of chain. This thing right here is called a functional group. So for example, if I did this is the generic representation of an alcohol, where you have an organic chain, a carbon chain with OH at the end. Those are our alcohols. So this functional group is called a carboxylic acid. It just has its name. And in fact, you know a carboxylic acid. Does anybody know who it is?
Acetate?
So this looks like acetate. So it's acetic acid. It's this guy right here. CH3COOH, right? So CH3, I'll write it out. Now, you're not always used to seeing it written like this, though it's written like this often because it's showing you how the elements are all bonded to each other. You're used to seeing it like this, probably HC2H3O2. Okay, but they're the same thing. There are 4 hydrogens, 4 hydrogens, 2 carbons, 2 carbons, 2 oxygens, 2 oxygens. These are the same substance. They're both acetic acid, but it's drawn like this. Okay, so look at, you have your acidic hydrogen attached to the oxygen. Okay, and the whole point is that the more electronegative this R group is, the more the electrons will be pulled this way, making it easier to pluck off the hydrogen. So like these two compared, we got fluorines over here instead of hydrogen, so there's a way bigger pull this way. So it's easier for this hydrogen to be plucked off, and that would make it a stronger acid than this one. Now, neither of these are strong acids. Just one is stronger than the other. They're both weak acids, but you can still talk about weak acids in terms of strength. Now, again, this is not a strong acid. It's just stronger than this one. Okay? None of your organic acids are strong. We have 6 strong acids. Everybody else is weak. Okay. All right, math time. So here we go. So obviously, if we're talking about acids and bases, knowing the pHs of their solutions are going to be important. Okay. So this equation right here is called the auto-ionization of water. So water hooks up with itself to produce your basic part and your acidic part. Now don't forget that this can also be called H+. Okay? They're interchangeable. So if I were to write an equilibrium expression based on this, I would write K equals products over reactants raised to their respective coefficients. Yes, this happens naturally. Okay, these mean the same thing. One has H2O plus, one has H plus. Now notice I didn't have reactants because they're liquid water. You don't put liquids or solids in equilibrium expression. So that's this right here. And they call it KW because it's the auto-ionization of water. And this is going to be at 25 Celsius, which is normal room conditions. Most of the reactions we do will be at 25 Celsius. I will show you down the road what happens to the scale when temperature changes, but until then, we're always going to assume 25 Celsius. You don't have to memorize this. If you look on your equation sheet, it's right here. Okay. H plus, or H3O plus, times OH minus is 1 times 10 to the negative 14th. So what is this used for? Well, basically you know K. K is 1 times 10 to the negative 14th. That's its number. All right. So what this is used for is if you know like hydroxide ion concentration, but you want to know hydrogen ion concentration, you would just plug in here and rearrange. Okay. Or if you knew hydrogen and needed hydroxide, you would just plug in there and rearrange. That's what it's used for, to jump from either hydrogen to hydroxide or hydroxide to hydrogen. Okay. Now, let's talk about where this number came from. 1 times 10 to the negative 14th. Well, by definition, we know that, we say that water is neutral, okay? And neutrality means hydroxide and hydrogen ion concentration have to be the same. That's what being neutral means. You don't have more acid or base. You have the same. So what are each of their concentrations in pure water? Well, 1 times 10 to the negative 7th molar. 1 times 10 to the negative 7th molar. Because 1 times 10 to the negative 7th times 1 times 10 to the negative 7th is 1 times 10 to the negative 14th. And they're equal when it's water, because water is neutral. And neutrality isn't defined by pH. Neutrality is defined by when the H plus concentration equals the OH minus concentration. That's what neutral is. Okay. So now we can take, so mathematically the P mathematically means opposite log. So we can take opposite the log of H plus and opposite the log of OH minus, and that gives us pHs. So pH, opposite log of this. POH, opposite log of this. So pH is opposite the log of H, POH is opposite the log of OH. And again, these equations are also on your equation sheet. Ooh, they're right here. Okay. So then what you can do, if you take opposite the log of this, and that's pH, and you take opposite the log of this, and that's POH, please take opposite the log of this and tell me what it is. It's 14, right? So that's where they got this equation right here. pH plus POH is 14. So like if you find POH, you can just subtract that from 14 to get pH. It's a really easy way to convert between pH and POH. And again, that is also on your equation sheet, so you don't have to memorize it. It's right here. Okay. So we don't need much of this right yet, but Ka times Kb is also the Kw constant. Ka, equilibrium constant for an acid, equilibrium constant for a base, equals the equilibrium constant for water, pretty much. So that is also on your equation sheet. So if you look over here, they say Kw equals this, and it also equals Ka times Kb. So what would you use that for? Well, sometimes they'll give you like, they'll give you like ammonia, and ammonia is a base, and then they'll give you a Ka value. You can't use a Ka value for something that is not an acid. You have to use a Kb value for something that is a base. So you would plug the Ka in here, you would divide, and that's how you could get the Kb if they don't give it to you, okay? So again, when you're working with acids, weak acids, you'll use Ka values. When you're working with weak bases, you will use Kb values. You will notice that you don't have Ka values for strong acids because they don't go to equilibrium. And you don't have Kb values for strong bases because they don't go to equilibrium. K stands for equilibrium constant. So you will never see K values for any of our strong species. It's only for the weak species. Okay? Then look at, if I take opposite the log of Ka, I get pKa. Opposite the log of Kb, I get pKb. Opposite the log of this number is 14. That's where they got this number. It's the rule of logs that when you do opposite logs of them, multiplying them is the same thing as adding them. I think we kind of talked a little bit about this. Was it in the kinetics chapter? This right here, this right here is the equation for a buffer. And we are not going to get to that for a while, okay? But this is the equation for a buffer. And it is also on your equation sheet somewhere. Let's see. Right here. We aren't going to get to this for a while. We're definitely not going to use this today, okay? Okay. So pH tells you the acidity of a system because H plus is what means acid, whereas pOH tells you the basicity of a system because OH represents base. So the scale, though, that you guys are used to using is a pH scale. Like, I'm pretty sure you've probably never seen a pOH scale. So we will reference the pH scale. So again, 1 is your really, really strong acidic acids, to 14 is your really, really basic, and 7 is considered neutral, which is pure water. And again, this is the pH scale at 25 degrees Celsius. This is not what the pH scale would be if we changed temperature, which we will discuss down the road. This would not be your pH scale. So again, neutral being 7 is only true at 25 Celsius. Neutral is not at 7 when you're not at 25 Celsius, and yet it's still neutral. Okay? Again, we'll talk more about that later. Okay, so let's do some math. Calculate the pH of a solution of 0.30 molar hydrochloric acid. So we're going to start to get into the process, or I try to ingrain this in your head, where you go through a handful of steps in your head when you see an acid or base problem. And the first step, step number 1, is to identify the major species. Now, I realize you think, okay, HCl is the major species, but that's not what I'm asking specifically. What is HCl? It is a strong acid. That is what I'm looking for when I say identify the major species. HCl, which is a strong acid. Because the next thing I ask you to do is to write out the reaction or the equation. Well, if it's just HCl, we just have HCl breaking apart, right? One-way arrow into the H plus and Cl minus. I don't see a reaction. It's just hydrochloric acid solution. So the thing is when we say it's 0.030 molar of HCl, it really isn't H of HCl, because HCl doesn't exist like this in solution. It exists like this. It's not floating around as HCl molecules. It's floating around as H plus ions and Cl minus ions. So when I say it's 0.030 molar of this guy, it really isn't this guy. It's this guy and this guy. So they're in a 1-to-1 ratio when it ionizes, right? So it's really 0.030 molar of this guy and 0.030 molar of the chloride. Now, the chloride does not determine the acidity of the solution, so I don't care about it. But I know hydrogen ion concentration, right? It's 0.030, so can I find pH? Sure. pH is opposite the log of H. What do we get? 1 something? Can you give me one more digit? Okay, so I hate to do this to you. It's not my fault. So this is 2 sig figs, right? So the rule of logs. So this is going to happen for PHs and POHs, or PKAs or PKBs, anything that have P's in front of them. Sig figs do not start till after the decimal. So this is a 2-digit number. The 5 and the 2 are the only significant figures in here. I did not make this up. It's not my fault. I don't know why. Don't ask me why. I have no idea why. So like, if for some reason this was your outcome, I mean, this is not possible with a PH, but if it was, this is a 1 sig fig number. Sig figs do not start till after the decimal for PHs or POHs. Okay, this is not even possible. I'm just showing you that that's how the rule works. Okay, now the question is, does this pH make sense? Well, HCl, strong acid, this is a really acidic pH. This does make sense. It's a very acidic pH for a strong acid. Okay, let's try another one. So calculate the pH of a 0.010 molar solution of lithium hydroxide. So lithium hydroxide is this. So identify major species. Yes, lithium hydroxide, but what? It is a what? Strong base. So what do strong bases do? So the next step is to write out the reaction. And it's not really a reaction because it's just lithium hydroxide, so it'll just ionize in solution completely, right? That's what the point of being strong is. Okay, so again, when I say it's 0.010 molar of this guy, it really isn't lithium hydroxide. It's lithium ion and hydroxide ion because it doesn't stay intact in solution. So it's really 0.010 molar of this guy and 0.010 molar of this guy. Now, let's just pretend. This is not true, okay? But let's pretend. If I would have where there's like 2 hydroxide, like calcium hydroxide or strontium hydroxide or barium hydroxide. Oh, thank you. Oh, thank you. What would I do? I'd have to have a 2 in front of here, right? Because it has 2 hydroxide ions if this happened. So what would this number be? Would it be 0.01? It'd be double this number, right? It'd be like if I called this x, we would call this 2x, right? So it'd be 0.01 times 2. It'd be 0.02 for the hydroxide. It's not. I'm just showing you that that can happen, like with your calcium hydroxide, strontium, and barium, because they have 2 hydroxides involved in them. And they're strong. Okay. So 0.01 molar hydroxide. So now I ask you to find pH. Well, in order to find pH, you have to have H, and I don't. So here's one. There are actually 2 ways to tackle this problem. I'm going to show you both ways. The first way is I do have this equation that has H and OH in it. H plus times OH minus equals 1 times 10 to the negative 14. It's on your equation sheet. So I have OH minus. So I just divide both sides, right? By 0.01. And that'll give me H plus. Pretty sure it's 1 times 10 to the negative 12 molar. So that's the H plus. Well, now that I have H plus, I can find pH, right? pH is opposite the log of H. So you end up with a pH of 12, I'm pretty sure. So I use my OH to get H, and then I can plug into my pH equation. I can't plug straight into my pH equation up here because I don't have H plus. pH involves H plus, not OH minus. So the pH is 12. Does this make sense? Lithium hydroxide is a base. This is a basic pH, so this does make sense. There is another way to do this, though. Anybody want to guess? So that's one way. What could I have done instead? If I know OH, could I find POH? Right? Because POH is opposite the log of OH. Okay, let's do that. POH is opposite the log of OH. And OH is 0.010. So POH is 2. Well, I know pH plus POH is what? 14, right? Always. So if I plug 2 in here, 14 minus 2 is 12. That way is kind of easier to me, but whatever. It doesn't matter which way you do it, but both ways will work. Any questions on that? Okay, let's try another one. Calculate the H3O plus. Now remember, H3O plus in this class and H plus are going to mean the same thing. And I give you a solution with a pH of 4.32. So you go, oh no. So pH is opposite the log of H plus or H3O plus. They mean the same thing. So this is going to require you to rearrange because I need to isolate the hydrogen ion. So first thing you want to do is move the negative sign over. So multiply everything by -1. So this negative is going to come over here. Now, you probably don't know this yet, or you might not. Does anybody know how to get rid of a log?
Exponent.
Exponent.
By 10?
Yeah, 10 to the x, okay? So if you look on your calculator, your log button, the second function of the button is the 10 to the x button because they're opposites, okay? So to get rid of a log, you do 10 to the x, so it gets rid of it. So 10 to the negative pH is H. So 10 to the negative 4.32 will give me my concentration. Now, pHs are weird for sig figs. This has a 2 sig fig number. Just the 3 and the 2 count. So concentration, though, is normal. So write a normal 2 sig fig number now, because concentration isn't funky, just pHs and POHs. I don't remember this number. 4.8 times 10 to the negative 5th molar. The 4.32 is negative because the pH equation equals negative log of H, so you have to move the negative over to isolate the H by itself. Okay. Okay. This one asks you to make a solution. So they want you to find the pH, and you're preparing a solution by dissolving solid in water. So before we even go to find pH, what can we find with this? The grams of potassium hydroxide and volume. What can we find out about the solution? Concentration, okay? That's what you need to know. Concentration. So how do you do that? Remember, concentration is molarity. Molarity is moles per liter. So we can find out the concentration of the potassium hydroxide solution. How do I do that? I turn the grams into moles. Using molar mass, potassium hydroxide is 56.11 grams per mole. That'll give me my moles. And then I divide by liters, so that would be 0.250 on the bottom. So the moles is 0.0356 something. And the molarity is like 0.142577 something. I'm not rounding yet because we're not done. Molar. KOH. Well, KOH is a base. So this molarity is for my hydroxide, right? So I could find POH because I know the hydroxide concentration. It's this number. So POH is opposite the log of OH, which is this concentration, 0.142577 something. So the POH is 0.84595 something. So you take 14 and you subtract that number, and you get 13.154 for the pH. Because pH plus POH is 14. So once you know POH, you can plug it in right here and subtract to get the pH. And this pH makes sense. This is a very basic pH, and potassium hydroxide is a strong base. So this was a little bit harder because I didn't start you off in concentration. I started you off where you had to find the concentration of the solution, and then you could do your math. Okay, now I need to show something to you. I'm going to have you just do a couple of practice calculations. I'm giving you hydrogen ion concentration, a couple of different ones. So this is hydrogen ion concentration. I want you to find the pHs of these solutions. So pH is opposite the log of H. I'm doing this on purpose. So you should notice that the numbers are just the exponent, the positive version of the exponent. So if the number out in front is a 1, perfect 1, 1.0, 1.0, 1.0, times 10 to the negative 12. The pH is just the exponent. The pH is just the exponent. The pH is just the exponent. If you remember, you're not supposed, there are parts of the test, the MCQ part, that you're technically not allowed a calculator, and they do expect you to be able to do this without a calculator. So that's why I'm showing it to you. So having said that, what was the concentration of hydrogen ion in water, pure water? Do you remember? The hydrogen and hydroxide were both the same number, is that right? They were 1.0 times 10 to the negative what? 7. So what's the pH of water? 7, right? And this was also the hydroxide ion concentration, right? Was also, so the pOH is also what? 7. What's 7 plus 7? 14. pH plus pOH is 14. That's where it came from. Okay. Okay. Now, it gets even crazier. I'd like you to calculate these guys' pHs. So now they're not beautiful. It's not like a 1.0 out in front, so they aren't beautiful numbers. This will work with pOH as well. So if this was OH minus, when this was a 1, that would be your pOH would have been 12, and your pOH would have been 3, and your pOH would have been 8. Yes, it totally works with OH minus as well. Absolutely. So I'm just trying to prove something to you. They won't, on the multiple choice test, actually make you calculate it out. So there will be one of two things that will happen. They will give you a range that the pH would fall in, or pOH if it was pOH, or they would give you a number that falls in the range. And here's what I mean. If you look at the exponent and you subtract 1 from it, that number, so 11 to 12, it will fall somewhere in between that number, somewhere between 11 and 12. It's 11 something, right? Okay, so look at the exponent. You subtract a number from it. The 1 less than 3 is 2. So the pH is somewhere between 2 and 3. It's 2 something. Look at the exponent. You take 1 away from it. It's 7. So the pH is somewhere between 7 and 8. So if I did this and I put a negative 2 here, and you're trying to find the pH would be somewhere between 1 and 2. That's kind of the trick without a calculator. Okay. Okay, so one last thing. Let's do these little practice multiple choice, and then we will be finished. Okay, so it says, which of the following ranks the 3 bases? Okay, so we have bases in the first problem. From weakest to strongest. So the weakest will be written first, and the strongest will be written last in our options. So if you look at this guy, A, has the greatest pH, and it also has the least concentration. What does that mean? It has the least amount of hydroxide ions present, yet it has a super high pH. That's a strong base. If you don't need a hydroxide ion to give you a high pH, you're a really strong base. So A is our strongest base in here, for sure. Now, so who do we get to get rid of? So option C has B as the strongest base, and option B has C as the strongest base. So B and C are out. Both of these have A as the strongest base. Okay? So now when you're looking at B and C bases, they have the same pH of 11. So it's not going to be pH that's the deciding factor. It's going to be concentration. If this guy is 2 molar, it means compared to 1 molar, you should have double the amount of hydroxide ions in here. So more hydroxide ions, and yet your pH is still 11? So that's your worst base. You have more of it, and it didn't make your pH be more basic, so it's not as good of a base. So that's why A is the best option. A is the strongest, B is in the middle, and C is the weakest. Okay. So the next one asks for ranks three monoprotic acids. Let's talk about what the word monoprotic. Remember, protic or proton is being referred to as the hydrogen ion in here. Proton, protic. Monoprotic means the acid just has one hydrogen ion. So like HNO3, HCl, Br, HClO4, just one H. So it wouldn't be something like H2SO4. That's called a diprotic. Or like H3PO4 is called a triprotic. We're talking about just an acid with one hydrogen ion coming off. Okay. So now for this one, we want the strongest to weakest. So strongest acid will be written first, and then the weakest will be written last. So let's look at our strong acid. So look, we've got acidic pHs. That's good. And if you look at this first one, this is like almost as low as it gets, right? Very strong acid and not very much concentration. So you don't even need a lot of it to give me a super acidic pH. So A is your strongest acid. So A should be written first. So that's option D and option A are out because they don't have A written first. So now, how do you pick between B and C? Well, they both have the same pH, okay? But option C, substance C, should have more hydrogen ions present because it's more concentrated. So it has more hydrogen ions present, yet it doesn't make it more acidic pH-wise. So this would be the worst or the weakest acid, would be option C. So it goes actually in order. A is the strongest, and then B, and then C. So letter option B is the best choice.